Bismillahirrahmanirrahim. Assalamu alaikum to all my dear viewers and my special students. Today, inshallah, I Halim Gul is going to discuss a very special topic of electrostatics, that what is the reason and what is the history of formulation of Gauss's law, and in which problems the Gauss's law is helpful for solving and give us a solution. And due to limitation of time, I am not taking your quiz points because I have a target of just 30 lectures for a completion of the FSC second year course. But at the end of Gauss's law, I will give you one special quiz, and by this quiz you will be judged that how much you learned from the previous 3 lectures. And after that, I will clarify a very special definition of voltage, and inshallah I will claim that you have not heard or such that type of definition at any site, and then differentiate the voltage between potential difference, electromotive force, and at the last I will discuss a very special application of electrostatics is capacitor, that and also derive the relations for the charging and discharging of a capacitor, and how much energy is stored in just a very simple and a very interesting manner, because I usually speak to that I am not teaching you physics. I will just make a physics interesting for all of you. So move toward our target. What is the use and what was the purpose of Gauss's law? In the previous lecture, we have discussed that electric flux is equal to E dot A. Mean, if I have some cross-sectional area just like this, and any charge is placed inside its boundary layer, so the flux will be calculated by the formula number 1. But the problem was created that how I calculate the electric flux for a spherical shape, just like the shape of Earth, because Earth is in spherical shape, and also the egg has a spherical shape. Just like I take the shape of a sphere in a simple manner, and some charge Q, I was also placed minus charge at the last of the topic, but here I will take positive charge, and many electric field lines are emerging from this positive charge. So the spherical body has not a cross-sectional area, but it has a curved surface area. So it was a difficulty for the physicist to calculate the cross-sectional area, and after that there was a much difficulty by calculating the net electric flux, because when I make the patches of this surface area, so many patches are formed from its surface area. Why I form its surface area into patches? Because I will form a cross-sectional area, mean I will form a flat area. So if I take, this is A1, this is A2, this is A3, and up to n number of patches. So what was the net electric flux. So the net electric flux, net mean total electric flux, will be calculated by EA1. I am taking E because E is in a symmetric form. Symmetric form mean it is uniform throughout the whole spherical shape, plus E A2 up to E AN. I have no information about the AN, and the AN is either 1000, 2000, but also approaches to infinite. So I apply a technique of mathematics. I pick a common E. So I A1 plus A2 plus A3 up to AN, and I have some special function in a mathematics called summation. Summation mean if any variable is sum up to n number, then I will use a symbol summation, but the summation is used for an, and here I use a subscript. I start from 1 up to n up to infinity. So I have a special formulas for the area of all the spherical shapes, and the sphere has an area of E. E is the electric field intensity, and area for spherical shape is 4 pi r square. And in the previous lecture I have also resolved the equation for electric field intensity, which is Q divided by 4 pi epsilon naught r square into 4 pi r square. 4 pi cancel with 4 pi, r square with r square, and I obtained just a very simple relation Q or epsilon naught, and he win a name in the field of electrostatics. And according to statement number 1, he formulated a law that if you have to calculate the electric flux as the at the surface of any closed body, but the limitation is that you have not take any open boundary of the spherical shape. You have a closed path. So for any closed path, the electric flux observed at the surface area is equal to Q or epsilon naught. So this can be formulated as the law status flux over the surface of any closed boundary is equal to, I will also write as 1 by epsilon naught times of the total charges present inside the body is equal to 1 by epsilon naught times of total charges present in the spherical shape. Here I will ask a very simple question, just like, for example, if I have two shapes, one is let's suppose R, other one is 2R, and third one is 4R, and I am placing some charge just like 2Q, and let's suppose here I place 3Q, and here also place 2Q. So in which figure the electric flux is observed at the boundary in a large quantity? It's a quiz for you. So this is body 1, body 2, body 3. So guess it. You have just 5 seconds. So many so many students will answer that this is the correct answer. So many much students, the option is figure 2. But the electric flux for any closed spherical body does not depend on the radial distances. It is also dependent on the charges present inside the body. So this is the correct answer. So after that we will move to world in which figures are in which systems the Gauss's law is applicable. So applications of Gauss's law. The first application is that, let's suppose I have some spherical body just like this, and if I have to calculate excess charges inside the spherical body or any closed conductor, means if I have to calculate excess charges mean either the charges are in efficiency or deficiency. Efficiency means more electrons, and deficiency means the electron will be in the less amount as compared to the positive ion present in that special type of body. So in any conductor, I have also explained in the lecture number 1 that any conductor or any body contain equal number of positive and negative charges, and if I arise some electric field here, so I will result net electric field is equal to 0. Is equal to 0 mean conserved, mean the electric field inside the MCQs is also repeated in so many competitive examinations, that what is the net electric field inside any conductor. So the electric field intensity is conserved. Conserved mean if I have to sum up all the electric fields created in that spherical body, but the limitation is that you should remain inside a conductor. So inside a conductor the electric field is conserved. So I will apply the Gauss's law. This is the statement of Gauss's law, and to calculate the excess charges inside a conductor, so I am using flux is equal to Q mean excess divided by epsilon naught, but the main formula for electric flux is EA is equal to Q excess divided by epsilon naught, and I have also discussed that the net electric field is 0. So the left side give me a 0 result, and when I multiply this epsilon naught with the right side, it also give me a 0 result. From the equation number 2, it is clear that we have no excess charges inside a conductor. Means what is the logic of the statement that any body is charged? So all the charges are present at the boundary of any spherical shape or any circular or any plane body. So excess charges will also present at the boundary of the conductor. So the second application is that if you have to calculate, if you have, for example, any spherical if you have any surface cross-sectional area, just like I have a gold plate or it is made of silver, and this plate has so many infinite number of positive charges. So what is the effect, or what is the electric field intensity observed due to this surface body? So I will place a conductor just like, and the conductor is pass the paper, mean the one side is in the upward and the other side is the at the back side of the paper, and electric field just like observing at this cross sectional area is E1, and I am taking E due to symmetry. Symmetry means the electric field lines are same at the same distance from any charge body, and here I take just like E, and it is the area A1 and this is area A2, but both the cross sectional area have a same cross sectional area, so I am taking A due to symmetry. So what is the second application of Gauss's law is to calculate the how much electric field intensity is observed if any positive charges are placed at any surface sheet. So the second application is to calculate the electric field intensity. So I am using the equation for the Gauss's law. Flux is equal to EA for the point 1 and also for point 2 is EA, and so much questions are arising in your minds that why I am not taking the curved surface area of this marker, because the curved surface area is perpendicular to the electric field lines, and when there is a 90-degree angle between the area and electric field lines, the cos 90 is 0 and I will obtain. So I just neglect these terms, and the electric flux for Gauss's law is Q or epsilon naught, and these will sum up E to EA, and I divide the 2A to the left side and I will result Q over 2A epsilon naught, and this term Q divided by any area give me a surface charge density. You have a mass per unit volume is a mass density, but when any charge body is divided by area, this is called the surface charge density. But when I am taking or dividing this Q divided by volume, this will be the volume charge density, and this surface charge density is denoted by sigma, a Greek symbol, and 2 epsilon naught. So here the result of electric field intensity observed due to the any surface sheet. The third, and I name this is equation number 3. The third application is that if I have two parallel plates just like, and one is positively charged, mean deficiency of electron, and the other is negatively charged, mean efficiency of electron, and some electric field lines are generated in this way, because electric field lines are always directed from positive toward the negative, and we have also discussed in the lecture number 2 which is available. So for the experience of electric field intensity due to these oppositely charged plates, I will place any cubical shape. Cubical shape mean I placed just like a book. So when I placed a book, the book has, this is the A1 and this is A2 surface area, and this is the A3. So I am using flux. So the electric field lines are perpendicular to the A1 and A2, just like I will consider the A3, so A3, but I erase the substitute E3 because here I have observed only a single parameter for area, and the electric flux which I have calculated by the Gauss's law is Q or epsilon naught, so EA, and when this A divided by the left side, it will result Q by A epsilon naught. And what is Q by A? This is the surface charge density, and surface charge density is a specific for any body, just like aluminium, copper, plastic, or some other bodies, and which is easily available on the internet. So sigma or epsilon naught. So this is the electric field intensity due to two parallel plates, and this is the electric field intensity just only for a single plate, and this electric field intensity is half as compared to the for the two oppositely charged parallel plates. So note it by just pause the video because I will move after that a very special type or special topic of electrostatics, which is capacitor, and voltage, and after voltage inshallah we will move toward the capacitor. We will derive the relations for its capacitance, energy stored by a capacitor, and how the capacitor are discharged and charged, and what is the main purpose of capacitor, because mostly students have no idea about the capacitor, that what is the purpose of capacitor used in our electric circuits which are used in the computer, monitors, or so many electronic devices. So I will move toward the other topic, which is voltage. What is voltage? Basically, voltage is the number of excess charges at any point. For example, if I have a plate just like this, plus, and I named this plate as A. So this plate A has 6 excess positive charges, but I will take some reference. So when I take some reference just like C, so this C is a neutral. Neutral mean a reference point, and the A has a deficiency of 6 electrons. So this plate or point have 6 extra positive charges as compared to this point C. So this is the simple definition of voltage, that the number of excess charges at any point as compared to some reference point is called voltage. The number of excess charges at any point with respect to some reference point is called voltage. And I will take the voltage, this is plus 6 volt. But if I take another point B, and here I place or make efficiency of electrons. So this plate have efficiency of 6 electron as compared to this point C, and I will take, this is the voltage A and this is voltage B, which is minus 6 volt. So the plate A has a 6 volt mean deficiency of 6 electron as compared to the neutral plate, and the plate B has efficiency of 6 electron as compared to plate C. What mean by the minus 6? If I move 6 electrons or 3 electrons, if I move 6 electron to the point A, then all the 3 plates will balance and no voltage is observed at any point. So what is the potential difference? Mean voltage difference, voltage difference between these two plates. So voltage difference is basically represented by delta V, which is equal to VA minus VB, and VA has a plus 6 and minus, and this minus of the for electrons. So minus minus will become positive, and I will observe plus 12, and unit is a volts. So you have always familiar about that the battery which was connected with the UPS systems is of 12 volts. So what is the meaning, physical meaning of this 12 volt? Mean that two plates has a difference of 12 electrons, 12 charges. If I move, how can I balance this plate as compared to the point B? If I remove 6 electrons from point B to the point A, this will balance, but after that, when I move another 6 electrons from point B to point A, then here I will observe minus 6. So basically this plus 12 volt mean if I move 12 charges either from point B to point A or from point A to point A, if I move 12 charges or 12 electrons from point B to the point A, the point A will get a same result which have the point B, and similar case for the point B. So how much, for example, if I move a one or I break some crystal in point B, and you are always familiar about the crystal, that crystal contain positive and negative poles, but when I break this crystal and I move this positive charge to the point A, I will require some amount of work. So how much work is done by bringing a charge from negative plate to the positive plate? This is called the, and this work will equal to the potential difference between the two points. So this work mean how much work is done by moving a charge, mean positive charge, between the two plates having some potential difference. So this work done on charge will equal to the potential difference. If I have a small potential difference between these 2 points, I will do small amount of work by moving this positive charge to point A. But if these 2 points has a large potential difference, then I will require or do so much work, because the work is directly proportional to voltage. And from here I will derive a unit for the potential difference. So delta V has a unit of joule, and here I will use a coulomb. So joule per coulomb is a derived unit for the potential difference, but I will name it is a voltage, which is the SI unit for the potential difference. So after that, if I just like when I move this positive charge from point B to point A, here I will add up one positive, and here I will add up one electron, and I will result 7 electrons, and here I will result plus 7 volt. So now the potential difference will be plus 14 volt. So after that we will move, if I move a single electrons from point A to point B, or from point B to A, so delta V, del W divided by Q. If I take two plates in which the potential difference is 1 volt. 1 volt mean here I have a positive charge, and this point mean point A is a neutral. Neutral means equal number of electrons and protons, positive charges. But if I break a crystal, and for a neutralization of the point B, if I move electron from point A to point B, so how much work will be required? So this work will be equal to delta V is equal to delta W by 1 electron, and the potential difference is 1 volt. So the 1 electron will multiply with the left side, and I will get, this is the work. So basically electron volt is basically unit of energy or work. And so many MCQs are frequently repeated in the competitive examinations, that what is the difference between volt and electron volt. Basically electron volt is the unit of work by moving an electron from a neutral point to a point where there is a deficiency of electron, and volt is the unit of potential difference between positive and the negative plate. After that we are moving toward the capacitor. So what is capacitor? A simple applications, inshallah tomorrow I will do some quiz points related to the Gauss's law, voltage and electron volts. And if I write one electron volt, so basically 1 electron is equal to 1.60 multiplied 10 power minus 19 coulomb into volt, and volt into coulomb is equal to joule. So 1 electron is equal to 1.60 10 raised power minus 19 joule. And here is a simple relation which inshallah will be used in the nuclear physics, where I have to convert the mass defect into the binding energy. But what is a capacitor? Capacitor is basically two neutral plates, but the condition is that these two plates are always taken as a conductor, means either you have to take of gold, aluminium, copper. So, and I name this is plate A and plate B, and both the plates are neutral. Neutral means they have equal number of positive and negative charges. So if I connect a battery, and you are always familiar about the battery, because the point having deficiency of electron is taken as a positive, and it is also taken as a higher point, higher, and here is lower due to conventional current, which inshallah we will clarify in the second chapter, electrodynamics. So this negative plate have a efficiency of electron, so this efficiency of electron pole attract the positive charges from the point B, because any neutral body contain equal number of positive and negative charges, and it is the condition for conservation of energy. So when I pick these positive charges, just these positive charges will move and collect at a point, negative point. So, and the battery has some potential, mean the battery will perform some work by moving this positive charge from lower potential toward the higher potential. So these positive charges, when move toward the positive pole of the battery, both have the same charges, so they are repelled by the positive plate of a battery and move toward the other plate of a capacitor. Basically, these electrons are extracted by electrostatic inductions. So in this way, some potential difference is created, and the potential difference is created due to charging or storing of electric charges between the point A and point B. So inshallah, in the next lecture, we will clarify that how much charges will be stored by a capacitor. And in this video, I have just defined the capacitor, the device of storing electric charges, but that phenomena used for charging of by a capacitor is electrostatic induction. Inshallah, we will meet in the next video, and the lecture 4 will be the last lecture of electrostatics, and inshallah after that we will do some numericals and some checkpoints of the electrostatics just for your judgment. Take care. Allah Hafiz.